In this video, we're going to talk about polar plot. Polar plot is a plot drawn between the magnitude and phase angle for an open loop system by changing the omega value from 0 to infinity. Okay? Similar to the Border plot, what we learned from the previous model. So it tells us the system behavior. So we can find out system behavior by using the polar plot. So that's the main advantage. When it comes to disadvantages, it can tell the impact of the individual components of an open loop system. If you remember, in Border plot, we draw the individual lines. Here we cannot do that, okay, by using this polar plot. As well as another important thing is it cannot specify whether the system is stable or not, and how many poles are stable poles and how many unstable poles are there. That we cannot tell by using the polar plot. The only thing we can tell is the behavior of the system. It's just another graph. So here he's asking about to draw the polar plot for 1 over s. So s is nothing but sigma plus or minus j omega. So here we are trying to find the system behavior with respect to the omega, change in omega. Here omega is variable, sigma is constant, so I'm going to ignore that. So s equal to j omega. So here g of j omega equal to 1 over j omega. Now, so we have the real axis and imaginary axis. That's the real axis and imaginary axis. Now, how this system, how the graph is going to look like, how the system behaves with respect to change in omega. Now, say if I take omega equal to 0, I can write this as 1 over omega at an angle of 90 degrees. Where did I get this? So we know that 0 plus j omega. I can write this as 0 plus j omega. So when I convert this into magnitude, or this is in rectangular form, when I convert this into polar form, I will end up with omega at an angle of 90 degrees. So this is nothing but 1 over omega at an angle of minus 90. So here we know that this is 0 degrees, this is minus 90, minus 180, minus 270, or you can say plus 90, plus 180, plus 270 degrees. Now I have g of j omega equal to 1 over omega at an angle of minus 90 degrees. Now, so we're going to draw the graph based on this. So what if omega equal to 0? Then gj omega equal to infinite, right? What if omega equal to infinite? So 1 over infinite is gj omega equal to 0. So if we look at the values in between, so basically when omega equal to 0, the magnitude of that plot is infinite and it has a phase angle of minus 90 degrees. So here is the phase angle of minus 90 degrees. That phase angle is constant. Even when I change the omega value, phase angle is not going to change. So it is starting at infinite somewhere here. I'm assuming that's infinite. And then when omega equal to infinite, this value becomes 0. So the graph for this is going to be look like this. So the y-axis basically represents, that is omega. This is basically omega. So this is omega equal to, the y-axis represents here, basically the y-axis represents magnitude. Okay, so here is this is the y-axis. So here omega, this is gj omega at this is infinite, that's a 0 magnitude. Okay, so this is the magnitude. Now here is the next example. The given system g of s equal to 1 over s square. Okay, so when I write it down, gj omega equal to 1 over j square omega square. We know that j square is nothing but -1. So basically it's going to be 1 minus 1 over omega square. Now when we draw the graph, look at the magnitude. So the phase angle is, it's supposed to be 0 minus 90. So here we have 0 degrees phase angle. Now when omega equal to 0, what is gj omega? Gj omega equal to infinite. When omega equal to infinite, gj omega equal to 0. Okay, isn't it a negative value, by the way? So when omega equal to 0, this is a negative infinite because that's a negative value. So that indicates that so this is the x-axis, this is gj omega. Okay, that's the magnitude. So that value is infinite, so it's going to be coming from negative infinite, and when omega equal to infinite, that value is approaching to 0. This is the graph for 1 over s square. Now another example, say if I have g of s equal to s. Okay, so basically g of j omega equal to j omega. S is nothing but j omega. Okay, when I draw the graph, so basically if we look at omega value and gj omega values, so if omega equal to 0, what is gj omega? 0. If omega equal to 1, gj omega equal to 1. If this is infinite, this value equal to infinite. So it's a linear. Okay, but there is no phase angle. I mean, the phase angle here is, so I can write this as omega at an angle of 90 degrees. So this is real axis, 0, 90, minus 90, that's 180 degrees. Now when we draw the graph here, so as omega increases, gj omega value increases linearly at a phase angle of 90 degrees. So the phase angle is 90 degrees, so it's going to be something like this. It's approaching infinity when omega approaching infinity. Okay, and when omega equal to 0, gj omega value equal to 0. So this is the graph for g of s equal to s. Here is the next example. In this example, he gave us g of s equal to 1 over 1 plus 2s. That's the given one. Okay, when I convert this into gj omega equal to 1 over 1 plus j2 omega. Now when I write it down in the magnitude and phase angle format, so here it is, the magnitude is square root of 1 square plus j square 2 omega square. So j square is nothing but -1. So I'm converting that into -1. We will end up with 1 over square root of 1 minus 4 omega square, and phase angle is tan inverse of imaginary over real, which is 2 omega over 1. Now what I'm doing, I'm taking this tan inverse to the numerator, so it will become minus angle. So basically it has an angle right there. Now I'm substituting omega value and finding magnitude and phase angle. Okay, so this is the real axis, imaginary axis. So here I have gj omega equal to 1 and phase angle is 0. So if I draw that line is going to be, I'm going to draw a dotted line. Okay, it has a magnitude 1. Okay, so probably gj omega magnitude 1 there. Phase angle, that's 0 angle, this is minus 90, right? Now at omega equal to 1, I'm taking a very big gap. At omega equal to 1, the x-axis and y-axis, I'm just taking magnitude. Okay, so this is the real magnitude, that's imaginary magnitude. At omega equal to 1, magnitude is 1 over square root -3. 1 over square root -3 is nothing but 1 over, so in the square root we have negative numbers, so I can convert that into imaginary, 1 over j square root 3. Square root 3 is nothing but 1.723, something like that. So imaginary 1.723 somewhere here. Oh, that's 1 over. So that value become 1 over j 1.732, that's minus j 0.577. So minus, so this is, that's the imaginary axis, so minus j is somewhere here. This is minus j 1.732. okay, and it has a phase angle of minus 63, so it's going to be somewhere, I mean, I'm not drawing according to the scale, but it's going to be something like this. Okay, now if I put say 0.5 here, that line is going to be you have magnitude and phase angle, it's going to be somewhere there. Okay, even if I put 0.25, it's going to be somewhere here. Okay, now if I put a very large number, magnitude is going to be 1 over very large number, so it's going to be very small, and phase angle becomes minus 90 degrees. So that means when omega value is changing, that magnitude is reaching here 0. So when I draw a real graph at omega equals 0, it's starting at 0 degrees and ending at minus 90. Okay, so this is the graph of 1 over 1 plus 2s. I'll stop this video here. I will make more polar plots in the next video. Thank you.